Let's kick off our next video installment. This video we're going to focus our time and our attention on how we go about solving differential equations. There are lots of ways to go about doing this. In AP Calculus, we're going to use some integration techniques. We're able to solve most of these problems through direct methods. For those of you that will go on to study engineering and science and mathematics in college, there are whole courses called differential equations where you study more sophisticated methods for either solving the differential equation precisely, generating a general solution or a particular solution, or in some cases you're approximating solutions. We've done this through Euler's method with the BC students. This should be something that's pretty approachable, pretty user-friendly. So let's get started. We have a differential equation is a derivative equation. It is an equation that relates the derivative back to the original function. Sometimes they're straightforward, sometimes they're a little more complicated. We're going to generally dig deeply into our algebraic manipulation tricks and our integral calculus tricks in order to solve one. So let's look at this. We've got this differential equation, dy over dx is equal to negative x over y, subject to the initial condition y of 1 equals 3. If we need to unpack this, well, we know dy over dx is equal to negative x over y. y1 equals 3, what that tells me is that if x is equal to 1, then the corresponding y value will be equal to 3. Because I have this is we're going to refer to as our initial condition. This will allow us to solve the differential equation for a particular solution versus a general solution. And you'll see in a moment what the difference between the two is. So we're going to start our approach to this differential equation by seeing I have dy, I have dx, I have x, I have y. One of the more common methods that we've studied is called separation of variables. In order to do separation of variables, our goal is to get everything that has a y or a dy in it on one side, everything that has an x or a dx in it onto the other side. If I see this as a proportion, then maybe cross-multiplying is the way that I want to go. That'll give me the new equation y times dy is equal to negative x times dx. On many of the AP exams, you're awarded the first point by separating the variables. So we've done that. Our next move is that we're going to integrate both sides, which is why it is key that you have everything that has a y in it on one side, everything that has an x in it on the other. If I'm going to integrate y with respect to y, that's going to give me 1/2 y squared is equal to the integral of negative x dx, which is negative x squared over 2, plus Charlie. We don't want to forget about Charlie, our constant of integration. We now have 1/2 y squared equals negative x squared over 2 plus c. We can go further. We can start cleaning this up. If we'd like to multiply both sides by 2, that'll eliminate your fractions. 2 times 1/2 y squared, we'll get y squared, equals 2 times negative x squared over 2 is negative x squared. 2 times c is 2c. Now, this next move might seem a little unusual. This isn't something we normally do in an algebra class, but in calculus, c is your constant of integration. We don't know what it is. It could be any arbitrary constant. So if c is a constant that we don't know, and that we don't even really care too much about, it could be anything. 2 times that is also a constant. And in our class, we call that Super Charlie. Super Charlie has the power to absorb other constants. So I'm going to rewrite this 2c as just c. Some textbooks encourage you to call this c1. 2 times c1, I'd then replace it with c2. According to the College Board, you can just jump from 2c straight to c. That's fine. I still have not solved this completely for y. I have not used my initial condition that y of 1 is equal to 3. We can do that now, or we can do it later. It doesn't really matter. I'm going to choose to do this now. If the point 1, 3 is on this curve, then that tells me I can replace the y value with 3. I can replace the x value with 1. That's going to allow me to solve for c. 3 squared equals 9. 9 is equal to negative 1 plus c. And we get that c is equal to 10. I can go back up to this equation where we had y squared is equal to negative x squared plus 10. If you'd like, you could rewrite this in a more familiar, maybe more friendly form. Depending on your comfort level, you could add x squared to both sides, resulting in the equation x squared plus y squared equals 10. Hopefully we remember from pre-calculus, this is the equation of a circle. This is a circle centered at the origin. There's no shift left or right. There's no shift up or down. The radius is equal to the square root of 10. So the solution to this differential equation, subject to this initial condition, would be the circle x squared plus y squared is equal to 10. That's how we go about solving most of these problems through separation of variables. Another technique that we study for solving differential equations is generating slope fields. And as the name implies, this is a field or a collection of slopes. We're going to use the same differential equation we used before, which was dy over dx equals negative x over y, to look at how this field is generated. So we can pick a point. If I selected the point, let's say 1, 1, I can evaluate my derivative. I'm going to evaluate dy dx at the point 1, 1. I'll replace x with 1. I'll replace the y with 1. I get that dy over dx at 1, 1 is negative 1. What that means to me, how this helps me to generate my slope field, is if I go 1 to the right, if I go up 1, I'm going to draw in a tangent line that has a slope equal to negative 1. That's what this guy over here represents. I like to write sometimes what the actual slope is. You don't have to worry, is this exactly negative 1? Does it look like it's negative 1/2? Does it look like it's negative 2? What is most important when you're generating your slope field is pay attention of the sign. If this is a negative, that line segment must be decreasing. If it's positive, we're looking for line to be increasing. Another thing that I learned this year that I didn't know previously is if you are given a differential equation and you wind up getting an undefined slope, so that means dy over dx, which is the fraction negative x over y, if that is undefined, well, the only way that that's going to be undefined is if my denominator is equal to 0. So the derivative, the slope of the tangent line, is undefined everywhere that y is equal to 0. Well, we actually don't draw tangent lines there. So if you notice on this slope field, all along the x-axis, which is where the y values are equal to 0, we have no tangent lines drawn. You do not draw vertical tangent lines ever. All of the sources I consulted say we don't do that, so we're not going to do that. You might notice in the graph, if you can see that, we have these horizontal tangent lines everywhere along the y-axis. The reason that we have that is if this fraction, if the numerator of this fraction is equal to 0, which occurs at x equals 0, then my tangent line will have slope 0, which means we have a horizontal tangent. Additionally, once we have generated the slope field, if you look at it very closely, if you can see it well, you start to get an impression of what the solutions will look like. If you can see this well, we have this line segment over here that has negative slope. If I follow this line segment down, right, as I start moving, there are other line segments that are directing me what to do. This one is decreasing, this one is increasing, so we start curving that way. This one is increasing left to right, so decreasing right to left. We're going to start curving this way. This line segment is also increasing left to right, so I'm going to keep following these tangent lines This one's horizontal. As I follow that, I get to this next one, which is increasing. I continue to increase, and eventually I get back to that. I'm a bad artist, but if you follow the tangent lines, what you're going to see is a badly drawn circle centered at the origin. The radius will change depending on the point that you start with. If I started with this point over here, I would yield a larger circle, still centered at the origin, but the radius is larger. And as I pick different points, I will get concentric circles. They all share the origin as their center. Radius getting larger and larger and larger. That's the power of the slope field. You can take a differential equation, whether you know how to solve it or not, using integration techniques. You can generate your little tangent line segments. You can pay attention to your tangent line segments and then use them as your guide to generate a visual solution to this. It's a great way to start a problem like this, and generally on the AP exam, when they ask differential equation questions, you will be asked to generate a slope field, and those are usually really nice questions. Great question to look out for and a nice way to pick up some easy points. All right, so let's jump right into this. AP question, this one appeared on the 2005 exam. It was question number 6, calculator inactive. I would hope that all of our AP Calculus students, when they are taking the free response exam, will at least quickly look at the questions and decide, is this a question that I should spend my time on? Are there easy points for me to pick up? Question like this, absolutely, there are easy points available for you. So we are given a differential equation. We are given, we're given some points. We are being asked on the axes provided to sketch a slope field for that differential equation at the 12 points that are given. What does that mean? We're going to take each of these points. So we'll take the point 1, 1. We will evaluate our derivative at the point 1, 1. We'll find the slope. We'll then draw a quick little sketch of a tangent line that has that slope, and we'll move on to the next point, and the next point, and the next point. We're going to have to do that 12 times, so we're going to look to do that quickly. In part B, we're told that y equals f of x is the particular solution to our original differential equation. We have an initial condition that f of 1 is equal to -1. We saw that in the earlier example. We're going to write an equation for the tangent line to the graph of f at that point. This equations of tangent lines we know how to do. We're going to need a point. We're going to need a slope. And then we're going to use that to approximate the value of f of 1.1. So without actually knowing the true function, we are going to use the tangent line to approximate that value. In part C, this is where we're finally going to get to do some integration. We're being asked to find the particular solution to y equals f of x. Means we're going to solve that differential equation, subject to the initial condition that f of 1 is equal to -1. So let's get started on our journey. Part A, on the axis provided, sketch a slope field for the given differential equation at the 12 points indicated. So if I am at the point 1, 1, if I evaluate my derivative at 1, 1, I'm going to get -2 times 1 over 1. My slope of my tangent line is -2. I'm going to go over to the point 1, 1. I'm going to draw in a tangent line with a slope of -2. So I want it to be a little bit steep, especially on the AP exam. I do like to write in that the slope is -2. I want to leave no room for doubt with the AP readers that I know what is going on. That's what my slope is. And we can continue with the same process at all of the points. We'll pick another point, the point 1, 2, dy dx at 1, 2 is going to be -2 times 1 over 2. -2 over 2 is -1. At this point, we have a slope equal to -1. So I want a line segment that is going to be not as steep as this one, yet still decreasing. That is going to be my example of a slope with -1. I have 4 points on the y-axis. All 4 of these points, what I know is that the x-coordinate is equal to 0. 0, 2, 0, 1, 0, -1, 0, -2. If I evaluate the derivative at 0, 2, I'll have -2 times 0 divided by 2, which is 0. I have a horizontal tangent line. Not only will I have a horizontal tangent line at 0, 2, I'll have a horizontal tangent line whenever the x-coordinate is equal to 0. So I pretty painlessly get 4 of my tangent lines drawn in. I can finish off the process rather quickly. I won't go through and do every single one of them. At -1, +2, you're going to have a slope equal to +1. At -1, +1, you're going to have a slope equal to +2. I want to draw this a little bit steeper than the one above it. I'm not being asked to draw a tangent line at -1, 0. If I was being asked to do that, I'd have 0 in the denominator. That would make your tangent line have undefined slope. Typically in the AP exam, they are going to avoid questions that require you to do that. We're at the next point, -1, -1. If I evaluate my derivative at that point, dy dx at -1, -1 will be equal to 2 divided by -1, -2. So I need a steep line with slope of -2. If I do that again over here, my slope is -1. I continue the process over here. At this point, the slope is +1. Over here at this point, the slope is +2. And we're done. That's it. That's part A. And we've just picked up 2 points. They awarded the first point based on looking at, did you get all of the horizontal tangent lines correct? The second point was awarded for the slope at the other 8 points. Good luck, good luck. All right, let's look at part B now. We're given that y equals f of x is the particular solution to that original differential equation. And also we have the initial condition f of 1 equals -1. We're asked to write an equation for the tangent line at 1, -1. Well, we've known since algebra that if I want to find the equation of a line, I first of all need the slope of the line, and then I need a point. My slope is what we refer to in AP Calculus. The slope of the tangent line is dy dx. I want to know the slope of the tangent line at the point 1, -1. So I'm going to evaluate my derivative. -2 times 1 divided by -1. -2 divided by -1. We get +2 as the slope. We also could have just looked back to our slope field in part A, but I erased mine, unfortunately. So we have the slope. This is the slope of our tangent line. 1, -1 is the point of tangency between the function and the tangent line. So I can use our point slope form, which says that the y value along this line is going to be equal to my slope, which is 2, times x minus x1, the x coordinate for my point, plus y1, the y coordinate for my known point. And I can leave this as y equals 2, parentheses, x minus 1 minus 1. That satisfies the first part of the question, which asks us to find the equation of the tangent line. Now, what we want to do is we want to use the equation of the tangent line to approximate the value for f of 1.1. I want to be very careful with my notation here. F of 1.1 is going to be approximated by our tangent line. This up here is the equation for my tangent line. We're not claiming that they're equal. What we're saying is we're going to use the tangent line to approximate this value. So f of 1.1 is approximately y of 1.1, which I'm going to find by just evaluating y. At that point, we get 2 times 0.1 minus 1, -0.8. And we're done with part B. As we mentioned in earlier videos, you could leave this 2 times 1.1 minus 1 and then minus 1 as a final answer. There is no need to reduce your answer any further.